Okay, so what's the proof of Riesz-Thorin? Well, let's say little f is in big F, so nice simple function. All right, so let's apply duality. So duality says usual LP prime duality that the LQ theta norm of TF is given by this supremum here. We're taking the supremum over all G, where LQ theta prime, the norm, is equal to 1. And by density, we can assume G is in big F. These nice simple functions are dense in all LP spaces. And as I mentioned before, I'm not writing RNs everywhere, but everything is defined over Rn. You can do this for abstract measure spaces, which is really nice. It gives you Riesz-Thorin, possibly where one of these one of these Lebesgue spaces are just little LP, or not little LP per se, but if you take a measure space as just counting measure on the integers, then yeah, you get basically Riesz-Thorin for little LP spaces. But anyway, right. So what we need to prove then, so we want this here less than or equal to this here. Okay. So to get that, we just need to prove this independent of G and F, where the LQ theta prime norm is equal to 1. Okay, and if we actually use the fact that T is linear and replace F with F over the LP theta norm of F, then we can assume that this norm here is equal to 1, and that's really not much to that. So if we can prove it in this case here, then certainly the LP theta norm of big F is equal to 1. So we'll have that T big F G is less than or equal to A0, 1 minus theta, A1 to theta. Okay, but what this whole thing really is equal to is, maybe I'll do this here. Yeah, thanks to linearity, it's really 1 over the LP theta norm of F. I'm not going to write the Rn, TF G. Okay, so this whole thing here is less than or equal to this. So multiplied by this LP theta norm of F, and we get what we want. So it actually makes things quite a bit simpler, as we'll see in a little bit. Okay, so now here's where things get really, really pretty, in my opinion. All right, so yeah, big F is just simple functions where that have finite measure support. So let's assume little f is such a simple function where the Lebesgue measure of all the EJs is finite, and here AJ is positive, and here, well, I'll write it like this. This is some complex number with modulus 1, so basically polar form of whatever coefficients are in front of these characteristic functions. Same thing here, this is positive, and this is equal to 1 in modulus. and again, and we're assuming, well, yeah, and the Lebesgue measure of each Fi is finite. All right, so let's do something clever here. So there's no ambiguity if I take aj and raise it to this complex power. So I've already said what a to the z is for any complex number z and a positive. So let's define this nice, actually entire function. So for fixed z, this is just some complex number. So for fixed z, this is also in big F. Again, it's a mouthful, but for fixed z, this is a complex number. Okay, and for fixed z, again, define gz to be the following, and this also is just some complex number. So for fixed z, this is also in big F. Okay, and one thing to notice is that 1 over q theta prime is 1 minus theta over q0 prime plus 1 over q1 prime. So I'll quickly show you where that comes from. It's actually, things like this pop up in PDE theory when you want to do kind of Sobolev inequality type stuff. Okay, so why is that true? Well, let's just check this. I guess I could make this for homework, but I don't know, kind of too easy for homework. All right, so by definition, 1 over q theta prime is 1 minus 1 over q theta. Okay, so we know what 1 over q theta is. In the statement of Riesz-Thorin, it's 1 minus theta over q0 plus theta over q1. Okay, and this is fairly easy to see, is going to be equal to, just kind of write it in a kind of clever way like this, q0 plus theta 1 minus 1 over q1. Okay. And this is going just to be equal to 1 minus theta over q0 prime. Let me make it a little better. 1 minus theta over q0 prime plus theta over q1 prime. So nothing too subtle there. All right, so finally, let's define I of z to be this function right here. Okay, so this is well defined. There's no issue there. Gz is an f. Fz is an f. Remember, one of our assumptions is that as long as we have stuff in f, big F, t of something in big F times something in big F is an L1. So for fixed z, for z fixed, this is an L1, so there's no ambiguity in integrating it. Okay? And you can prove, and I think the easiest thing to do is Morera's theorem, using Fubini's theorem and Morera's theorem. They often combine together in a very harmonious way to prove that things like this are holomorphic in a nice domain. Like, for example, proving the gamma function is holomorphic. That's, you usually use Morera's theorem. So I'll leave this as a homework to prove that this is holomorphic on the strip. The real part of z is between 0 and 1, and it's bounded and continuous on the closure, on the closed strip. Okay, so there's no claim that it's uniformly bounded for all f and g in big F. But for fixed F and fixed G, this is going to be holomorphic. Well, it's holomorphic and bounded and continuous on the closed strip. So when I say no uniform, I'm not saying it's not uniformly bounded for F and G, but we don't care. And also, if you really think about it, this function is not that funky looking. T is linear. So what you could do is get rid of this. I mean, I'll just do it because otherwise I would just give you a hint to do this. Okay, so, right, so for fixed Z, this is a constant, this is a constant. So what, thanks to linearity, Tf of Z is just this whole sum here, T applied to this characteristic function. So you can take TFZ, multiply it by GZ, you get a kind of ugly double sum, but you basically just get, well, a sum of m times n pieces that are each in L1, because T times this characteristic function, T applied to this characteristic function times this characteristic function by assumption is going to be in L1. That's our assumptions. T applied to something in big F times something in big F is an L1. Right, so basically I gave you a hint how to use Riesz's theorem to prove that this is holomorphic. And I gave you basically how to prove that this is bounded and continuous on the closed strip. All right, so we're going to apply the Hadamard three lines theorem to this holomorphic function. Okay. Right, so let's say m theta is exactly what we had before, except applied to I. Okay. So by Hadamard's three lines theorem, I of theta and modulus, for any theta between 0 and 1, well, it's obviously less than or equal to m theta, because m theta, well, it's the supremum of all y, so in particular, if we set y to be 0, we get I theta in modulus. That's going to be less than or equal to m0, 1 minus theta, m1 theta, and again, theta is between 0 and 1. So basically, all we need to, I claim that we're basically done. I claim that Hadamard's three lines theorem basically proves it. So maybe first, before I do anything else, I should have probably done this earlier, but why the hell is it called the three lines theorem? Well, basically this picture says it all. We want to approximate the modulus of f on this line, the real part of z is theta, and we can do that in terms of just these other two lines, or by, we can do that, approximate f and modulus on this line, real part of z is theta, by doing that on just these two lines, real part of z is 0 and real part of z is 1. Again, it's amazing that if we do it on these two lines, we get any other line in between these two lines. That's why it's called the three lines theorem. Okay, so let's just read off of let's just kind of unravel what this whole thing is really telling us. So first of all, let's get what I theta is. Literally, just what is I theta? Well, let's plug in z equals theta. Okay. So that's this here. Remember, it was 1 minus z. Okay. But sorry, I don't want this here. This. Right, but remember that 1, So let's get rid of this here. Too close. So 1 is going to be equal to just multiplying both sides by p theta. 1 is p theta times this whole mess here. So let's put that to good use to get us that this whole thing here is equal to 1, the exponent. Okay. So this is just aj beta j. So I want to make sure. So actually, it should be aj alpha j, not beta j. A little typo there. So it's really alpha j. But anyway, sorry about that. But this is what f is. So f theta is f. And similarly, g theta is g. So I theta is just the integral we want. Okay? So now we're getting somewhere. We have this integral that we need to estimate, and we hopefully can estimate it. We hopefully the stuff on the right here is exactly what we want, and it is. It turns out to be exactly what we want, which is, I'm going to claim that, I'm going to claim that what I have in this box here is going to be exactly this, here. It's going to be exactly this. Okay, and let's just do a little bit of unraveling and see why this is true. Or rather, it's less than or equal to this here, what I have in the box. All right, so let's see why that is true. Okay, so let's do, let's say the real part of z is, or let's say theta is 0. Okay, so we're looking at z is 0 plus iy. So let's assume x is an EI and just unravel what this equals. Okay, well, yeah, just plug in z is 0 plus iy. Okay, so first of all, let's remind you that this is going to be e to the z ln of a. And so this is going to be e to the real part of, whoops, sorry, forgot the e here, real part of z ln of a. This is the, this is e to the real part of z, because a is positive. And that's exactly just right. So right, it's a to the real part of z. Okay, so that's really important here. Okay, so we can throw out this imaginary stuff because we're taking modulus here, and this, remember, has modulus 1. Okay, so the only thing that's real is p theta over p0. Okay, well, when x is an EI, f of x is alpha j, aj alpha j. So in modulus, f of x is just aj. Right. So really, this, if you're in doubt, just go back, and there really should be no doubts here. But right. So because f is just some of these characteristic functions, I should say I'm assuming that the ej's and the fj's are all disjoint as I can when I write a characteristic function. So this is equal to modulus of f of x to the p theta over p0. And again, because if x is an EI, modulus of x is just AJ. Really AJ modulus AJ modulus alpha j, but this equals 1. Okay. And similarly, we get this equality here. Okay. So let's use Holder's inequality to this integral here. So I have an integral right here. So if I just use Holder's inequality, this is just TFZ LP, sorry. Let's do it with respect to Q theta. So it's LQ theta prime. And I should mention, basically implicit, but I'm doing the case where Q1 and P1 are all finite. Very easy modification to what I'm doing handles the case where Q1 is infinite or P1 is infinite. Riesz Thorin doesn't really say anything if both of them are infinite. But anyway, all right, so yeah, just Holder's inequality says this is true. So let's put that to good use here. Right. Okay, so z is 0 plus iy. Okay, well, we have a bound. So sorry, I think I did Q theta. I want Q0 for Holder's inequality. Yeah, sorry about that. And we want that because I know something about this integral here. Okay. What do I know about this integral here? Well, I know because fz is in big F, I basically know that t, well, I have a bound for this what I just circled. Okay. That's one of our major assumptions of the Riesz Thorin theorem, that we have this nice bound here. So I can, this is, so just going back here. Yeah, I have this nice bound here for F and big F. That's our assumption. So, right, we get A0, same function here. This is a function in big F. Okay. Right, but now I claim that these two are going to be equal. Okay. Well, why is that true? So let's just unravel this here. I'll do it right here. So this is going to be the integral of, got enough room here. Well, let me make this a little bit smaller. Perfect. Okay, so, right, so this is going to be f of x p theta over p0 raised to the p0, 1 over p0. Well, the p0s cancel. I don't have room for the x, and this should be dx here, but I'm running out of room. So this is p theta. I'll write it as 1 over p theta. Well, I mean, I gotta really, sorry, this is p theta. So let's write this as p theta over p0. So these p thetas cancel, but the point here is that this is LP theta norm of F. and here it's p theta over p0. Okay, so we get this here, and basically the same argument, not really an argument, but just compute this, you get the LQ theta prime norm, but we are assuming both of these are 1. So this is equal to a 0. We came to we had this reduction that we can assume this LP theta norm of F is 1, and by duality, we're assuming the norm of G on LQ theta prime is 1. Okay, and you do the same thing for the M1. So we look at Z is 1 plus IY. Sorry. So it's a little messy here, but this is one whole thing here. So again, we throw out everything that's imaginary. All that is real is kind of funky to say that, but well, it's really what's real is p theta over p1. Okay. And so again, because the EIs are disjoint, this is going to be absolute value of f of x, or modulus f of x to the p theta over p1. Okay, again, we're throwing out all this imaginary stuff because it has no contribution to the modulus. And similarly, okay. So I should mention, this is one of the most clever, it's a very, very, very clever proof. I think Riesz had a very difficult proof of this, and then Thorin came along and gave this little like 2-page proof that everyone thought was just the most clever and genius thing they've ever seen. Right, so now we again do the same Holder's inequality, but with respect to the exponents q1 and q1 prime. You can check, well, anyway, yeah. So sorry, again, there's modifications if, very easy modifications if q1 or p1 are infinite, or if q1 is 1. Well, if q1 is 1, q1 prime is infinite. Very easy modifications handle that. But anyway, right, so again, we use the other bound we have for t, okay? And then same kind of thing we did before. This is going to be equal to this LP theta norm of f, LP theta prime norm of g, which is just a1, okay? So the conclusion is that putting all these pieces together, this is I theta, rather like this. This is equal to this here, and we said this is equal to M0 thanks to Hadamard 3 lines theorem. And M0 is less than or equal to A0. Sorry, this is M1 right, M1 is less than or equal to A1. So we get exactly what we needed to prove. So this is a very technical proof, but again, this is really how, what you really do is somehow try to abstract everything I've done to make it easier to reapply it in different contexts. But essentially, when you boil it down, you basically repeat these arguments to a large extent to prove a version of Riesz-Thorin theorem for all these spaces that I mentioned and variations of them, Hardy space and variations thereof, Bergman space and variations thereof, Fock space and variations thereof, et cetera, et cetera. So in that sense, this is a very important proof. Yeah, as I said, having these versions of Riesz Thorin for these different spaces is incredibly useful. I've needed it in my research and for a variation of the Fock space, and did exactly this for a variation of the Fock space. So I want to finish off by making an important comment about the Riesz Thorin theorem. So as I mentioned before, basically the proof that we, or at least I mentioned before rather, that the Riesz Thorin theorem holds for arbitrary measure spaces, so LP spaces over arbitrary measure spaces. And the proof is literally the same. There's no difference. And what's in particular very important is when your target space is an LP space over the integers with the counting measure. So you get basically a little LP. So in other words, when T actually spits out sequences, okay? That's extremely important, and it's important enough for me to really state Riesz Thorin for operators that go from LP to little LP, particularly LP of 0 to 1. And of course, it's not very subtle that we have Fourier series in mind. So let's say S is the collection of all sequences of complex numbers where K, sorry, this should be AK is 0. Okay. So it's a set of all sequences where AK is 0 for all but finitely many K. Okay. So in other words, it's sort of like the sequence analog of a simple function with support with finite measure. Okay. Okay. So basically, yeah, the AKs are all zeros except for finitely many Ks. So the theorem is as follows. Let's say theta, P0, P1, et cetera, are all as before, no different. Let's say I have a map from simple functions on 0 to 1 to S that satisfies these two inequalities here. Okay. So basically the same thing as before, except instead of a big LP space, this is a little LP space. Okay. And this is for all F in all F. So big F of 0 to 1 is just the vector space of simple functions on 0 to 1. It's obviously redundant to say the simple function has finite measure support because 0 to 1 has finite measure. Okay, then we have basically the same conclusion. That we have this norm bound for the interpolated LQ theta and LP theta norms. And we're interpolating between this, Q0, P0 norm bound and this Q1, P1 norm bound. Okay. So like I said, you could take the proof of Riesz Thorin, just do everything we did for an abstract measure space, abstract measure spaces, and this is a consequence of that. It's probably instructive to just go through the details and reprove this. I'll make that as a homework just to make sure we're all on the same page on whether we understand the proof of Riesz Thorin. And I also want to mention the proof of Riesz Thorin we gave is actually very important because what you sometimes do in analysis is you want actually not to just look at T, but you want to look at a family of operators that analytically depends on a parameter Z. So it's like TZ is a family of operators where Z is in the same strip. And if you set conditions on TZ so that, you define this I of Z function in basically the same way. Sorry about that, wrong. So if you set conditions on TZ so that you can use the Hadamard three lines theorem with respect to this function I of Z, then you basically get a very powerful extension of Riesz Thorin for such an analytic varying family of operators. And this is called Stein's interpolation theorem. If you go further in harmonic analysis, you'll hear the name Elias Stein over and over and over again. He's one of the giants of 20th century harmonic analysis. He only recently died, maybe a year or two ago. But yeah, and so if you put the proper conditions on this family of operators that depends analytically on Z, for Z in the strip, then exactly the same proof as I've presented here works. And I believe actually, yeah, Terry Tao has a very nice blog entry on Stein's interpolation theorem. He was a student of Elias Stein, actually, Terry Tao. So I'll maybe put that in the comments, a link to that blog post. But anyway, so, right. So finally, let's put this to good use, what I just described. Basically, this LP to little LP kind of Riesz Thorin theorem. Okay, and we can use it to prove the Hausdorff-Young inequality for Fourier series. And I'll leave this for you to do. It's virtually the same as the proof of Hausdorff-Young for Fourier transform. And because the proof is so identical, if you Google Hausdorff-Young, I would say a lot of times you're going to get Hausdorff-Young for the Fourier transform, and a lot of times you're going to get Hausdorff-Young for Fourier series. It's because the proof is so similar, we often don't really, Hausdorff-Young refers to either one. So Hausdorff-Young is, if P is between 1 and 2 and F is an LP of 0 to 1, then the sequence of Fourier coefficients is in little LP prime. And in fact, because we have that F hat is an isometry from L2 of 0 to 1 to little L2 of the integers, and because we have a trivial L infinity, right, we have a trivial L1 to L infinity, big L1 to little L infinity bound, we basically get the same, virtually the same, it's the same consequence, or rather the same conclusion as Hausdorff-Young for the Fourier transform, in that basically, your A0 and your A1 is just 1, so it's 1 to the 1 minus theta, 1 to the theta is just 1. So the stuff you get from applying Riesz Thorin is just 1, and hence it's stated like this. Just the LP prime norm of the sequence F hat is less than or equal to, sorry, this should be the, this should just be the LP norm of F. Okay. Right, so the LP prime norm, the little LP prime norm of f hat is less than or equal to the LP norm of f. Okay. Yeah, and again, you should check check the setup. Redo the setup and check for yourself using this version of Riesz Thorin. Yeah, the only thing maybe that takes a little bit of ingenuity is to not much, but is to really define apply Riesz Thorin as stated here to the truncations of your sequence of Fourier coefficients, so that after, let's say, for k, for my absolute value of k bigger than big N, everything's 0. And then you can just let n go to infinity. But anyway, all right, so new homework is coming soon. Hopefully this was interesting. And yeah, so from now we're just going to go further in the LP theory of Fourier series and the Fourier transform, which will lead us to, as I mentioned before, the Hardy-Littlewood maximal function, Calderon-Zygmunt decomposition, Marcinkiewicz interpolations theorem, some very powerful tools that really are the cornerstone of modern study of Fourier transform and Fourier series. Okay, all right, yeah. So that's all for that. So long. Take care. Bye bye.